Thank you. Good morning. So this is joint work with Claude-Guy, Quimper, and Hélène Verhaeghe. Check. Sorry. Okay. So I get a call from someone who wants to sample solutions of a CSP. No, not really, but I'll still tell you why we should care about the sampling solutions, why that can be useful, and why it's not so simple when you want to do it right. Then I'll tell you about our uniform sampling approach, give you some empirical results, and conclude with some remarks. Okay, so you're given some constrained combinatorial space, and you want to sample the solutions, its elements, uniformly at random. Now, that can come up, applications for this could be for hardware, software, black box testing, where so you've got a set of valid inputs, not any input is valid, and you want to make sure that you produce the correct output. Now, you've got too many inputs to try them all. So you want to try some, so you want to sample, and ideally you want to sample representative inputs. So that could be an application. Also comes up in algorithmic fairness, where you want this set of solutions, or at least a sample when there are too many. So here you're not solving a constraint satisfaction problem. You're not looking for just one red needle in the haystack. You've got a bunch of needles in a huge haystack, and you want to sample so that you get a solution has equal chance of being being selected. And if they have some properties, you want somehow your sample to be representative of the solution properties. To keep it simple, let's say we've got red needles. We also have green needles in your haystack, and so you'd like your sample to be representative of the proportion of red and green needles. Okay. So we want to do this in CP. So we have a model with discrete variables, each with its domain. We have constraint relations constraining the combination of values for those variables, and any valid assignment to the variables, well, is an element, a solution element in that space. Okay. Well, why don't we do it simply? So we just pick a variable uniformly at random, pick a value in its domain uniformly at random, and go from there. And maybe look at solutions once that choice, that branching decision, has been done. Sure. Okay. So here pictorially, you've got green and red dots, those solutions. And if you consider the vertical axis as being the one for xi, so you're really taking a horizontal slice in your set of solutions by selecting that value. Okay. Well, you'll get uniform partitioning. Every solution, a given solution, has probability 1 over the size of the domain of the variable of being selected. Fine. So maybe you're lucky and that slice here, that blue slice, that plane there has the right proportion of red and green, but maybe you're very unlucky. And maybe most of the green solution, maybe all of them, happen to be lying in that plane. So you'll get, your sample will over-represent the green solutions for sure. So what you're lacking is pairwise independence. So the probability that a solution, lies on that plane, given that another solution, another green one, lies on that plane, well, it's not 1 over the size of the domain. There may be some correlation, and maybe quite high or quite low. Okay, so doing it in this simple way doesn't really work well in practice. Can be disastrous, as we will see later on. So what do? Well, this is where universal hashing comes in. And that approach has been used first on SAT models. So it's been used for model counting, an early paper, 2013, then for sampling. And what they use are random parity or XOR constraints. So instead of having a very sparse constraint, just one variable equal to a value, it's over the whole set of variables. That helps. So for SAT models, binary variables, random XOR constraints. For CP models, how it generalizes, so you've got larger domains, is random linear constraints in modular arithmetic. Okay. So here's another picture. Again, the dots are the set of solutions. And so you're taking this random linear constraint in modular arithmetic. So for some coefficients randomly selected, a1 times x is congruent to 2 modulo 5. So here, so you've got these, again, these planes, these hyperplanes in arbitrary orientation. And here is just not one of them, it's all of these, right? So every 5/5 slice, you're taking the solution. So you're expecting to have 1 in 5 solutions that way. And then you can add another one, the red one. So those are the red hyperplanes in an arbitrary orientation, mod 5. So you're expecting 1 in 25. So those would be the purple dots here would be the ones that would be both in the blue plane and the red plane. Okay, so that's pictorially, that's the idea here of how you do the sampling. So we've got the nice thing is that we do have here probabilistic guarantees. We didn't have pairwise independence before. Here, thanks to other people, previous work, we do. So we will have a system of linear equality constraints in modular arithmetic. Okay. And so M, so let's say we have in general M equalities, coefficients chosen randomly, and a prime modulus P, at least as large as the domain size. Okay. And with that, so these people have shown that, so given two solutions, x1, x2, you have uniform partitioning. So that's, you had that before. So 1 over the chance of a x1 being satisfying this constraint is 1 over p to the power m. You have m of these, right? The multipliers we saw 1 over 5, 1 over 25 when p is 5. But you also have pairwise independence. So the chance of x1 satisfying the constraint, given that x2 and other solutions satisfy the constraint, is still the same. Okay, that's the nice thing that you want to have. Okay, so we have that. But we need a bit more than just equality constraints, because this controls, the size of our of our sample, the proportion of solutions we pick. While if P is largish, that's pretty crude, right? You can't really control the size of your sample so well. So we also need modular inequality constraints. And basically, that's from a paper last year. You get the same two properties that are important. And what's important here is that you see the numerator here is just not 1. It relates to the right-hand side of the of your linear inequalities, basically, right? If it says equal to c sub I, well, it could be equal to 0, 1, 2, all the way to c sub I. You see where that product comes from. So that gives you, freedom to select the right sample size that you want. Okay. So that's with inequalities, great. So let's look at our sampling algorithm then. So the overall idea is, well, you're given a CP model. Then the first step is the trickiest, if you want. We want to determine the right mix of equalities and inequalities to get the sampling fraction we want. So what we do is we'll say, so for some lambda between 0 and 1, we'll say, okay, I want, 0.1. I want 10% of the solutions, or more likely, 1/10% of all the solutions. So that's your lambda, and that's what we want to get. So you don't know how many solutions there are, but you want a sample that has, that fraction of the solutions. So you'll need to determine the right mix of equalities and inequalities so that the fraction we saw before in the probability, the right-hand side is the right one. Then it gets very simple. You just generate those random equalities and inequalities. You add them to your model. So that shrinks its solution space to the desired size, basically. And then with the nice properties, well, it's not just shrinking the search space, it's the solution space also, the same fraction in probability. And then you just enumerate all solutions in your remaining cell. I mean, if you look at those intersections of planes as a cell in that subspace, you just enumerate the solutions, that's your sample. Okay. So step 1, finding the right mix. Of course, I mean, if you want the details there in the paper, but basically looking again at this. So this is the right-hand side we have for the inequality, for the modular inequalities. Now here, see, you've got, so this product is over M prime and you've got M here. So So we're looking for a number of those modular constraints, m. M prime is the number of inequalities among those. So the rest are equalities, and that sort of spells out this product here. So you want that to be close to lambda, your desired sample size. So we'll look to factorize the numerator so that it's close enough to lambda times p to the power n. Now the factorization, don't be scared by the factor. I mean, those are we're using small numbers, so any factorization, I mean, there's not an issue here. We're not factoring very large numbers, okay? So that's what we want to do. So an example here. So say we want 2% of solution. So lambda is 0.02 and p is 11. Maybe your domain size is up to 10. So you're picking the next prime, 11. And so that will give you, for example, here, m equal to 3. So I will use 3 constraints. Your factors, so your numerator is 27, 3 times 9. So we factor it here as 9 and 3. So we'll have 2 inequalities. One corresponds to this right-hand side, the other one here. And out of 3, so there's 1 equality as well. And if we compute this, you see that the relative error is below 1.5. So we can get, pretty close. And actually, we use an epsilon. We decide how close we'd like it to be. Okay. So that's the first step. And then, you just generate. So from the same example, you had the P11, M3, and those 2 factors. So you'll generate 1 equality, modulo 11. So you generate randomly the A1 coefficients and the B1, they're the right-hand side. And then 2 inequalities. Now recall that we had in the numerator was C sub I plus 1. So it's minus 1. So here it's not 9 and 3, it's 8 and 2. And so you add these to so you generate this, then you add it to your model. And then you just generate, you use your favorite branching heuristic, doesn't matter. You have a new CSP, you just generate all your solutions, okay? As a bonus, and that you'll see that comes into play later on in the results, you won't get any duplicate samples in one sampling. So you've got your search space and you enumerate the solutions. Of course, these will be distinct in one run, right? Which is not a given if you're using, say we have the set of solutions and you pick solutions with a pseudo-random number generator. Well, maybe you'll hit the same one twice. Here you don't. Okay. There's one step I skipped, and I'll come back if I have time because that's all very nice. But what do you do? We want to do filtering on those constraints. What do you do? That's partly previous work, but if I have time, I'll come back to it. Okay. So we will skip over that and go to the experiments right away. Okay. So we use a few benchmark problems from previous related papers on sampling and model counting. So D and Queens, a graph coloring instance, features models, that was from another paper, so two from there, and some synthetic instances where you know how many solutions there are, you can control it. They've got a nice combinatorial structure. Okay, who do we compare against? So we'll compare against an oracle. So suppose that you can first generate all the solutions. That could be very time consuming, but suppose you have them, and then you're using a pseudo-random number generator, you just pick solutions uniformly at random. Not so uniformly, but okay, because your random generator is not perfect. But that would be, it's not really, you will see a best case scenario, but you've got all the solutions, you pick them. Okay. The other one, random table, is from a paper last year at CP. So they generate random table constraints, but on a small number of variables, typically from 2 to 4. Okay, definitely not the whole set of variables, and that comes into play. So they don't have any guarantees about uniformity, and in practice it can go bad, chiefly because you're on a small set of variables. I mean, it's not as extreme as what I showed you before, just picking one variable and fixing it to value, but it's close to that. So it can go bad, as we will see. Okay. Okay, graphs here. So we generate a bunch of samples. So x-axis is number of samples, and we track how uniform it is as we go. Just higher curve, higher is better, right? Closer to 1 at the top is better. You will see throughout the gray lines are our approach here with different lambdas, basically. The oracle is in blue, and the yellow is the random table, the other approach. Here we have an extra curve, the red one with different parameters, because you have to pick up parameters. Here the number of variables on which the tables are generated is different. But you'll see for the rest, it'll just be the yellow curve with their recommended parameters. Okay, so synthetic instances. You see that, well, the blue, so the oracle is not perfect, see? It's even going down there. As I said, that's strange because you would think, okay, the oracle, that's the standard. Well, no, because there are imperfections in the random number generators. And it's not the actual generator we use. We've currently trying a bunch of them, and they all have, they're not perfect. So the results vary, but there's none that's so well performing. But you look at, so where are our curves? Well, they're all here actually at 1. Okay, or very close. Here it gets a bit lower on these. See, you've got the black one that's a bit below. We're using the same random number generator. Why is it better? Well, it's the fact that, every time, so we generate a bunch of samples, but every time we generate several samples and they're all distinct, right? And that helps. That helps being more uniform. The random table approach is not too bad on these, right? But yeah, it's doing fairly well. Okay. And queens. Here's another one where the random table approach did fairly well, the yellow curve. The oracle is doing a bit worse, actually. And we're doing, well, about the same here. If we're sampling, 1%, 5%, the black curves at 25%, understandably, because we're sampling, picking a big chunk every time, we're basically at 1. Okay, I think my pointer is gone. Okay, graph coloring instance on the right. There are many solutions. See where lambda is quite small here. It's at the bottom. We're still doing the black curve quite well, better than the oracle, much better than the random table, which is, getting quite low here. Okay. Finally, those other instances here where these are from the random table paper, and it's doing quite badly here. The yellow curve just dips and is gone. We're still doing fairly well. If you look compared to the oracle, and here, we're close, especially here if we do lambda is 25%, but even the other ones are pretty good. Okay, you don't have the bad behavior. So in practice, it seems to be doing quite well. Okay, but what about, is it very time consuming? Maybe the random table, well, random table doesn't have any guarantees, but maybe at least it's much faster. Well, not that much. So here we're for instances that have quite a few solutions. You have the number of solutions here. You have the sparsity or the density of the solutions. And we look at the ratio, so of the competition with respect to ours. You can see that for the oracle column. So, wow, it's no big surprise, but we can be much faster because they need to enumerate all the solutions. That's very time consuming. And we're more uniform in practice anyway. With the random table, different number of variables in their tables. For n queens, they're faster and they're doing pretty well. For the others, though, it can be about the same or more time consuming. And again, you don't have uniformity. So that sort of settles it. Why is it doing better for n queens? And we're not, we suspect it has to do with, because it's not the number of solutions, it's the sparsity of solutions. Here you've got very few solutions. I think that's a factor here. It's not that worrisome because typically you want, the cases you have lots of solutions and you want to sample because it's just too many to enumerate. So that's not so, that's still fine. Okay, to conclude, and if you want to know about ask me a question if you want to know about the filtering, I won't have time. Takeaway message. So this approach is simple. Right? You just add constraints to your model and then you do what you want. You don't need a special branching heuristic or whatever. It's uniform. You see that you've got some probabilistic guarantees and you see that in practice it seems to be behaving quite well. So because your linear modular constraints partition space of solutions evenly. It's efficient even against a non-uniform approach. We see that we're not paying that much of a cost in general in terms of computation time. And precise, we're finding the right mix of constraints so that we do have a sample size that is the desired size. Follow-up work, well, we're currently experimenting with a larger set of benchmarks to see how to better delineate its strengths and weaknesses. And we're looking at applying for software testing and the kidney exchange program. I mentioned algorithmic fairness. Well, there's a fairness there of who gets a kidney in the transplants. And at least in one approach, having all the solutions, engineering solutions is an important aspect, but if there are too many, if you sample, you can still do something. Okay, that's all. Thank you.
Questions? So in the motivation, you mentioned that this analogy of red and green needles. Do you have some sort of equivalence classes on the solutions here as well, or how is uniformity measured? Because if I assume just one solution having some probability, it occurs.
Well, you want any solution to have the equal chances of being sampled.
Okay.
That's
you don't.
So if we sample, in the graphs I show you, if we sample, 100 times the number of solutions, while we want the expected numbers, you want every solution to be occur about 100 times. That will be perfect uniformity. Yeah. Yeah.
So maybe a follow-up.
Yeah.
Specifically, how does symmetry come into effect here, right? So if we want to sample non-symmetric solutions. Now, if the underlying CP model is breaking symmetry, then you should get it in some way, right? But is there another way to do that? Because that could be the equivalence class.
Yeah. Oh no, I haven't looked into that at all. Yeah, I don't know. But in the end, you're getting this CSP with the additional constraints, so you can.
Yeah. So if the underlying CSP is symmetry breaking, then you should get it for free.
Yeah.
How does the number of constraints that you want evolve with respect to the parameter lambda?
Yeah, in practice, and so 3, 2, 3. That's what I've seen. That's what unless you've seen something else, Hélène, but no, it's small. It's small. Yeah, because you don't need so many constraints to reach the accuracy, the sample, to approximate your lambda in practice, and what we've tried.
First question from Zoom.
Okay.
What happens is if you have different types of variables with different domain size, for example, cell times and machines in the scaling models?
Yes. Okay. So what happens if you've got different types of variables and different domain sizes, and even in the review, someone said, "Well, what about auxiliary variables?" And so I said over the whole set of variables, basically, you're generating those constraints over your decision variables. So possibly a subset of variables that fixes a solution. That's what you're branching over. If they're different domain sizes, well, P would have to be at least as large as the largest domain size. One thing I didn't mention that's nice is you sort of want as many equalities as, okay, that's a lead into. Let me just quickly say, okay, for equalities, you can use Downshot and Elimination because you've got a field here. So so you get a parametric system, you simplify it into that, and then you need only to branch on the parametric variables. So you're reducing the dimension of your space. So the more equalities you have, the better it is. So you're getting that as well for your branching heuristic. You're getting actually those parametric variables to branch over. And I forget why I wanted to mention that. Yeah, and auxiliary variables, so another problem. Yeah.
You remember by the coffee break, you
Sure. Okay.
Let's thank the speaker again.